Okay, in this problem, we have a uniform electric field. Uniform electric field simply meaning that the electric field stays constant from one point to another. So look, hey, sit down. So look, the electric field here, 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 it's the same. It doesn't change. The only place you're going to find that is between oppositely charged parallel plates. If you have a positive plate and a negative plate, there's going to be an electric field in between, and the reason we know that is if you stick a charge in there, if you stick a charge in here, that charge is going to get a force. What do electric fields do? They exert force on charged particles. And by the way, how do we define the direction of the electric field? It's the direction that a small positive charge wants to move when placed in the field. Look up here. So here we have a little positive charge. The force on the positive charge is that way, which means that's the direction of the electric field. Okay. Now, when would you have a non-uniform electric field? Just so you understand the difference. A non-uniform electric field would be like this. You got a big point charge like this. Electric fields going out like that. Are these electric fields constant? As you move away from the charge, what happens to the electric field? It gets smaller. Okay. Okay, so the information we have in this problem, they're talking about a beam of electrons, but notice that they say each electron. So we're gonna focus on a single electron. Okay, so this guy right here is an electron. In the upper right-hand corner, I have information for the electron, which the problem assumes that you have. I would give that to you on a test. I'll give you the charge of an electron and the mass of an electron. Now they tell us, so they say, what is the magnitude? What is the magnitude of the electric field pointing in the direction of the electron's movement? So if the electron is moving in the direction of the electric field, what's going to happen to the electron? We'll just look at the situation here. They're telling us that the velocity of the electron is in the direction of the electric field. Does the electron want to be moving that way? No. So it's very similar to throwing a ball up in the air. You know, if you throw a ball up in the air, what happens to the ball? It goes slower, 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 stop, and then comes back. And that's exactly what's going to happen here. This electron is going to go slower, slower, slower. It's going to stop, and then it's going to shoot back again, right? So they tell us the initial kinetic energy. This electron has a kinetic energy of 1.6 times 10 to the negative 17 joules. Right here, the velocity goes to 0, so it has no kinetic. And what else do we have? Oh, we know the mass of the electron. Okay, so the first question, what's the magnitude of this electric field? Oh, we have the stopping distance. From there to there is 10 centimeters, which is 0.1 meters. Okay, that's the stopping distance. So for part A, the way you're going to find the electric field is with the equation for the force of an electric field. So what's the equation for force of an electric field? QE. Okay, so rearrange that. E is going to be the force of the electric field over Q. So do we have the charge that applies here? Yeah. Well, what's the charge we're talking about? It's the charge of a electron, which is 1.6 times 10 to the negative 19 coulombs. So all we have to figure out now is what? The force. Now, by the way, which way, as the electron moves, which way is the force of the electric field? To the left. It's going to be away from the negative plate towards the positive plate. So how do we get the force of the electric field? Well, the easy way to do it is to go like this. So one of the equations from first semester, net work always equals what? Change of kinetic. It's kind of a useful equation to know. So that's going to be kinetic final minus kinetic initial. Okay, what's kinetic final over here? 0. So kinetic final is 0. We have the kinetic initial. And by the way, what is the net work here? How many forces are doing work on the electron? As the electron goes from here to there, how many forces did work on it? Just one, the force of the electric field. Or were you thinking gravity?
No, because wouldn't each electric field have a force in it?
Oh, this is all one electric field. All these electric field lines, it's all the same electric field. Yep. It's all the same electric field. Okay, so what is work net? Work net is going to be the work of the electric field, so that's going to be equal to negative kinetic initial. Okay, what is the work equation? What's the work equation? Force times displacement. You shrink this down. We're on. Okay, so the work of the electric field is going to be force of the electric field multiplied by the displacement equals negative kinetic initial. So the force of the electric field is going to be negative kinetic initial over delta x. So negative kinetic initial was 1.6 times 10 to the negative 17 joules. The delta x is 0.1 meters. So this gives us a force equal to 1.6 times 10 to the negative 16 newtons. Okay, now why does it make sense that this comes out negative? Because look at, to the right is plus, to the left is minus. Which way is the force of the electric field? To the left, so it makes sense that it comes out negative. Okay, and by the way, the charge is also negative. 1.6 times 10 to the negative 16 newtons. So this ratio right here comes out as 1,000 newtons per coulomb, which is the electric field. Now, how else could you have found the force of the electric field? What you could have done, F net equals what? MA, and what's the only force acting on the electron? The only force acting on the electron is the force of the electric field. So the force of the electric field equals MA. So then you just solve for A, but to do that, that's multi-step here. You got to take this kinetic, convert it to velocity. Can you convert kinetic energy into a velocity? Yeah, because what's the kinetic equation? 1/2 mv squared. So you can figure out what the velocity is. Once you have the initial velocity, realize you have the stopping distance. You can use a kinematic and find the acceleration. Okay, part B. To do part B, so here's the electron. We have some initial velocity, okay? And then over here, the velocity goes to 0. The stopping distance from there to there is 0.1. What they want us to find is the time. We're looking for the time. So to do this, you have to figure out what this initial velocity is. So how do we do that? Kinetic equals 1/2 mv squared. So V is going to be square root 2 kinetic energy over m. Here's the mass right here, so plug that in there. Plug this in there. So the initial velocity is 5.93 times 10 to the 6. So from here we can do a kinematic. To find the time, go like that. V final is 0. So T is going to be 2x over V initial. 2 times 0.1 over 5.93 times 10 to the 6. So this gives us 3.4 times 10 to the negative 8 seconds. Okay, and then for the last question, after the electrons stop, what will they do? So the electrons go like this. They go slower, 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 stop. Are they just going to sit there? What are they going to do? They're going to shoot back with the same acceleration, right? The acceleration through this whole situation is the same. So they will accelerate back towards the positive plate, is what they do.